Hey everybody. For those of you that don't know me, my name is Pravesh, and this is going to be an introduction to the course Analysis of Algorithms, or COMS 2015. It's great to have you guys back in class. I guess we'll be communicating a lot more often again. My email address is listed at the bottom there, pravesh.ranchard@wits.ac.za. But I'm pretty bad with email, and I find that using the WhatsApp group is probably the most convenient way to get in touch with me. Okay, so looking at the title of the course, Analysis of Algorithms, you're probably thinking, what is this thing? So this lecture will cover some of that. But before we get into that, I just want to go through what the course structure will be like. So the first thing is that we'll have lectures every Tuesday at 8 a.m. All that means is that I'll upload a lecture at some point before Tuesday 8 a.m. so that you can look at it. There are labs and tutorials on Thursday and Friday. These are hand-ins that you'll have to do on a continuous basis as the course proceeds. The tutorials will mostly be theory type things. This is a very theory heavy course, and the labs will be programming. The tutorials and labs will be mixed. So I might ask you to do a tutorial on a Friday or a lab on a Friday, or that sort of thing. There's no clear structure on which will happen on a Thursday or a Friday. And they'll be concurrent with computer networks. So what will happen is that you'll have tutorials and labs for both courses at the same time. The course has a book that you can download from the Moodle course. And the book is free and open source. So if you'd like to print it out, because you find it easier, please do. And we'll be following the structure of the book pretty closely. So at any point, if you want to read ahead, you can do that, and you'll be ahead of the game in the course. So the title, Analysis of Algorithms. What is that? What does that mean? Well, algorithms are fundamentally just procedures to solve problems. So this course is pretty much just a course on problem solving. And we've done some of those logic puzzles in mobile computing, and there'll be some more in this course. And here's the first one. So the first logic puzzle is the egg drop. So how this puzzle works is you have two eggs of equal strength. Okay, so they both will have the same breaking point. Okay, and these are pretty strong eggs, so we know that they can take a pretty heavy fall without breaking. Okay, so you want to find out how strong these eggs are. Right? And how you want to do it is that you have a 100-story building, and you want to find the highest floor from which the eggs can be dropped without breaking them. Okay, and you only have two eggs. So I'll give you some time to think about this. So hit pause on the video and give it some thought, and then I'll talk some more as soon as you unpause. Okay, I assume you've unpaused me now. So the difficulty about this puzzle is not so much that we have to figure out at what point the egg breaks, right? How we could do that is we could drop the egg from the first floor, like one of the two eggs, and if it breaks, we know they break on the first floor, and if it doesn't, we could go to the second floor, right? And we could drop it from the second floor, and if it breaks, we know they break from the second floor, and then we could do the third floor, and so on and so forth. At some point, the egg will break, and we'll know that that's the first, so the floor from which it breaks is the lowest floor on which the egg would break if we dropped it, right? So if we go down one floor, then we'd get the highest floor from which the eggs won't break. So for instance, if we dropped it from floor 60 and we found that it broke, but we were going floor 1, 2, 3, 4, 5, then we know on floor 59 it didn't break, right? So floor 59 is the highest one from which the eggs can be dropped without breaking them. So we have a solution. Great, we've solved the problem. The next thing we want to try to do is to find a way to do it using the least number of egg drops. So in the worst case of the previous solution, it could take 100 drops to figure out what floor we can drop it from without it breaking, right? Because maybe it only breaks on floor 100, and then we'd have to drop it on all the floors up till 100 until it broke. Okay. And we can do a lot better than this. So I want you to come up with ways to to do it that will require a lot less egg drops. It's quite, I think one of the first things to try and think about is how you could do it with 50 drops in the worst case rather than 100. And then you can come up with better and better solutions. And I'd love to hear your solutions as well. So the course is about problem solving, but that seems a bit wishy-washy. So what we're going to do is we're going to make it a lot more concrete. So the first thing we're going to talk about is what constitutes a good solution to a problem. So we've got this problem and we've come up with something that solves it. Now, is it a good solution? Well, the first question is what makes it good? If it's good, why is it good? There's three characteristics we're going to look at in this course. The first one is correctness. Okay, that may seem like a straightforward thing of saying, it's not a good solution if it's not correct, right? So if it gives you the wrong answer, it's a bad solution. But that's a bit too simplistic. So sometimes we've got problems that are so complex that we say, yeah, maybe it's wrong, but it's approximately correct, and we're happy with that. Okay, so correctness is not as clear cut as it initially appears. Obviously, the aim is a solution that's correct in all cases and exactly correct in all cases. But sometimes we have to settle for a problem that's exactly correct in some cases and incorrect in lots of others. Sometimes we have to settle for a solution that's approximately correct in all cases and occasionally completely, exactly correct. So we'll talk about correctness as this course proceeds. The other thing we talk about is efficiency. So in the logic puzzle we had earlier, we said, look, we could drop this egg 100 times, but that would be a bad solution because it would just take really long. So when we talk about efficiency, what we're trying to figure out is this a quick way of solving the problem? And we'll talk about how we measure what quick means in this context. So is this solution as fast as it can be? And the last characteristic is generality. So remember, in every previous interaction I've had with you guys, I've emphasized that one of the defining characteristics of computer scientists is that we're really lazy. Okay. Now, what generality allows us to do is it allows us to be lazy because we can say, when we solve a problem, we don't want to just solve that one problem that we were particularly interested in at that time. We want to solve a whole class of problems, right? Why this is useful is because then if subsequently I have a problem that's sort of equivalent, I've already solved it. I don't have to do any work, okay? So we'll look at how to solve problems in a general way so that they apply to lots of different specific instances rather than just the one we're looking at immediately. Now, all of this is well and good. We talked about correctness, we talked about efficiency, we talked about generality. But these are kind of meaningless unless we can ensure that the properties hold. So meaning when we say something is correct or approximately correct or exactly correct in some cases, can we prove that that's the case? So when we talk about correctness, what we'll be looking at is proof techniques. You guys have probably seen proof by induction, proof by contradiction, stuff like that in math. Now, what I found is that often when you're doing this as part of math, you just sort of memorize some proofs and you write them down. We're going to look at what the procedure for using these proof techniques is, and we're going to make you good at coming up with your own proofs. Okay, so what that means also is in terms of the assessment of this course, you'll be required to be able to prove things that I didn't give you the proof of, right? And a lot of that is about not blindly implementing proof techniques, but understanding why they work and what's useful about them. Okay, that may seem a bit scary, but it shouldn't be. Like, we'll cover it in the course. Think of it as one of the outcomes of the course. So if you don't already know how to come up with an inductive proof or a proof by contradiction yourself, that's fine, because that's what the course is meant to help teach you. When it comes to efficiency, we'll look at complexity analysis. So I think in Richard's course last year, you already looked at big O notation. which describes how an algorithm's runtime grows with the size of the problem, right? So complexity analysis is a very important part of this course and will help us determine whether our algorithms are efficient, okay? In terms of solving problems with generality as a measure, we'll look at solving abstract rather than concrete problems. So what this means is we'll try and take out all the implementation details of a problem basically and try and reduce it to its simplest form. And we'll be using graphs as a technique to make this happen a lot of the time. Okay, so in terms of the ordering in which we'll do things, we'll solve a bunch of problems, but we have to have the basics in place first. So the first thing we'll talk about is complexity analysis. Again, I know you guys did some of that with Richard last year. We'll then look at graphs. Again, I think you did some of that with Richard. Graphs are a collection of nodes and edges, or vertices and edges, where a set of vertices are connected to each other by edges. You'll find that I'll use the word vertex and node, or vertices and nodes, interchangeably. Some of the problems we'll be looking at include scheduling, using an algorithm called graph coloring. Interestingly, this is how your exam timetable is calculated. It's using an algorithm to solve the graph coloring problem, which is a good way to do scheduling. We'll look at algorithms around matching, which are ways of sort of assigning resources or potentially assigning item X to person Y or something like that. We'll look at path planning. So if you've got a set of vertices and edges, can you find good ways of getting from one vertex to another? You can picture it like a GPS. If you've got towns and roads, path planning is sort of saying, can you figure out a good set of roads that gets you between particular towns? We look at project planning using PERT charts. This is a graph-based algorithm for managing projects and is widely used in managing software projects, so you could find yourself using them a lot. And we look at fault tolerance. So this is sort of saying, how do we plan so that when stuff fails, we don't have a complete system failure? Okay, and this is just a high-level outline. You'll get much more in-depth explanations of these problems as we go on. Okay, so the first thing we're going to talk about is complexity analysis, and it relates the problem size, which we call n, to the computation time. Okay, what do I mean by it relates the problem size to the computation time? So basically what it tries to do is it tries to say, how will the computation time grow as the problem size grows? So for instance, if I was looking at sorting a list, say, what I'd want to know is, as the list gets larger, how does the computation time grow? Okay, so for instance, let's say I said to you that the algorithm or the problem I want you to solve is to return the first item in an array. Okay, just always exactly the first item in an array. If the array is of size 1, that would take us no time, right? It would be immediate. We just take the first item out and print it. If the array is of size 1,000,000, what would we do? We'd still just take the first item out and print it, right? So the amount of time it takes to run this algorithm doesn't change with the problem size, right? So we'd call it a constant time algorithm. On the other hand, if I had an algorithm that said print out every item in the list, then if the list is of size 1, it's going to have to print out one item, which will take not that much time. But if I have 1,000,000,000 items, then I have to print out 1,000,000,000 items, and so suddenly it will get large, right? And so what I found is that as I change the problem size, that computation time changes. How much it changes by depends on the algorithm itself. And that's the really useful thing for us to know. Now, why we care about this is because, so you use your computer all the time, right? And you've probably upgraded your computer a few times. So you started out with a computer that was fast for the time, but by now is probably incredibly slow. And as you've gone through time, you've got faster and faster computers. When I was a kid, I had a Commodore 64, which operated at 1 megahertz. okay? And, 1 megahertz now is not even a real way to measure the speed of a computer. It's ridiculous. So computers have gotten way faster. But you'll also find that when you use a faster computer, it's not that you suddenly have a computer that's just way too fast for you. Why is that? Like, why when you get a faster computer, it doesn't feel faster? Well, the reason is because when you get a faster computer, you generally want to use it to solve bigger problems, right? If you get this huge gaming rig with like a really good graphics card and stuff like that, you're not going to be playing everything on low detail and low resolution. You're going to bump up the detail and the resolution, right? So when you get a faster computer, you want to solve bigger problems. Okay. And that's great because we're saying, well, the problem size can increase. Okay, but how much can it increase? So if we had an algorithm that was linear, like say the one we had 1 billion items and we wanted to print them all. If we have a computer that's just fast enough to do that without frustrating us, then it can print out 1 billion items. Now we get a computer that's twice as fast. So it can print out 2 billion items in the same time, right? So that's pretty great. But that's only true because the problem is linear, meaning the growth of the computation time grows linearly with the problem size. But it's entirely possible for algorithms to grow exponentially, meaning the runtime of the problem can be expressed as something like 2 to the n. Okay, don't worry if this is not entirely clear. We'll cover it in detail. This is just a basic introduction. But let's say we said the runtime is governed by the equation 2 to the n, meaning if I had a problem size of 1, it would take 2. If I had a problem size of 2, it would take 4. If I had a problem size of 3, it would take 8. If I had a problem size of 4, it would take 16, and so on, right? So let's say my current computer can solve a problem of size 1 million, right? So that's great. It can do 1 million items. If I get a computer that's twice as fast, that means I can only do 1,000,001, a problem of size 1,000,001, because that takes twice the amount of time, because the equation is 2 to the power 1,000,001, which is twice 2 to the power 1,000,000. Okay, so this complexity analysis, by relating problem size to computation time, also helps us understand what improvements we're going to get from having faster and faster computers. Now, generally, we only care about performance where the problem size is large. Okay, so meaning, like when I say it relates the problem size to the computation time, I don't care about when the problem size is like 1 or 2 or 5 or something like that. Because generally, if the problem size is small, I can use any algorithm. So let's say I have like 5 different algorithms that can sort a list. If my list is of size 5, I shouldn't even waste time deciding which algorithm to use. I should just pick any algorithm because they're all fast enough, right? When I want to do an analysis, it's because I have a very large list and I need to make sure that it works fast, So I only care about very large N. Okay, and one of the things we'll talk about in this course is that when we're doing this analysis of how the problem size grows with computation time, there are a number of things to keep in mind. One is that there is uncertainty, meaning sometimes I just don't know. Like my algorithm is just too hard to analyze. So sometimes I say, I don't know. I don't know. How fast is it? I don't know. But maybe it's better than exponential, or maybe it's better than some other algorithm. So I don't know how fast it is, but I know it's better than this other one. Or I don't know how fast it is, but I know it's worse than this other one. So that helps me model uncertainty. I can establish upper bounds and lower bounds and say, look, I don't know exactly where the complexity is, but I know that it's in some range, it's within some bounds. Another thing I have to model is the characteristics of the underlying data. Okay, so for instance, let's say I told you that I want you to find the smallest number in a list. if the list is unsorted, you'd have to go through all the items and find the one that is the smallest. But what if the list is sorted? Then you just have to take the first item out and you're done, right? So there's certain underlying characteristics of the data that establish what the best case and the worst case for the algorithm is. So like in terms of an algorithm that maybe has to find the a particular item in a list. So let's say I said I'm searching for the item 10 in a list that has 1 million items. If the first item is 10 and I decide to search from the first item, it's just going to take me one comparison, right? I'm going to look at the first item and I'm going to see it's at 10 and I'm going to say, okay, cool, it's found. So in the best case, that only took me one operation. But in the worst case, the 10 might be in the last item or not in the list at all. So if I'm searching the list for the item, I go all the way through it and just never find a 10, and it takes me tons of time. Okay. Another thing we're going to talk about in terms of complexity analysis is what data structures we use. So you saw in Richard's course that if you used a linked list versus an array, you got a completely different complexity result for the same algorithm. Okay. So this is important, that the complexity of an algorithm is also related to its implementation, right? Meaning if we use a particular data structure, the algorithm will have a different complexity to if we use the completely different data structure. Okay, all of that was just a summary, and when we get to the complexity analysis lecture, it will hopefully become a bit more easy to understand. Okay. Then when we talk about solving abstract problems, one of the tools we're going to use is graphs. And some examples of graphs are on the slide, and graphs are just made up of vertices or nodes and edges. And you can see that sometimes the edges can be directed, meaning they have arrows, and so it can point, you can only go along an edge in a particular direction. And sometimes they can be undirected, meaning you can go in either direction, represented here as there being no arrows. Sometimes these edges can also have weights, so they can have numbers attached that are hopefully meaningful in some way. Perhaps they're the length of a particular road or the cost of some item. But we will often transform our problems into graphs. And the reason we do that is because lots of similar problems can be transformed into the same graph problem. So we'll often find like thousands of real world problems mapped to the same graph problem. So once we've solved the graph problem, we've accidentally solved thousands of real world problems, which is great because we're lazy, right? So instead of solving the other 999, we'd prefer not to, right? Because what's easier than solving a problem? Not solving a problem. And so like just as an example, one of the first ones we'll look at is something called graph coloring. And basically the problem says what you want to do is you've got a graph and you want to assign a color to every vertex such that no two vertices that are neighbors share a color. So meaning like in the first, or say in this first graph, you can see vertex 2 is attached to vertex 3. So they can't have the same color, but 2 and 4 could potentially have the same color, right? Now that seems like quite an abstract problem to solve, right? Assigning colors to vertices such that no adjacent vertices share the same color. But we can use this to solve multiple real world problems. And we can do that just by sort of replacing the nouns in the sentence. So I said I want to assign colors to vertices such that no two adjacent vertices share the same color, right? I could similarly say I want to assign timetable slots to colors such that no two courses that share a student have the same timetable slot. And then I end up with your exam timetable, okay? And the advantage is a bunch of real world problems will all map to the same abstract problem, okay? In an example like fault tolerance, what I'm looking at is if I remove a vertex from a graph, does it disconnect the other items? So if I removed vertex 3, can I still walk from everywhere to everywhere? Yes, I can. But if I remove vertex 4, for instance, I won't be able to get from 3 to 6 or from 5 to 6 because I can only get to them going through vertex 4, right? Now, that's very useful when designing things like networks, because you might want to say, if one router goes down or one computer goes down, I don't want the system to become disconnected. But it can be useful in a whole range of problems. So we did some research a few years ago on methods to reduce the spread of HIV. And one of the techniques we used was using the same algorithm for fault tolerance to try and figure out which vertices would disconnect the graph. And what we were trying to say was, if we target particular people for more education or circumcisions or condom use, can we stop the spread of HIV by disconnecting the network, by disconnecting the particular nodes that are keeping the network connected? Okay. And I'll talk about that more when we get to that part. But it's interesting that, network design versus reducing the spread of HIV, and yet they're the same graph problem. Okay, so back to some more concrete stuff. You will be required to submit your tutorials online. So the theory type questions that you're going to get every week, you have to answer them online and they will be marked. Labs will also require you to implement solutions every week. This isn't a programming course, but there is tons of programming required. Okay, so mobile computing was the programming course. This course is fundamentally a theory course. Don't expect it to work similarly to mobile computing. It's very different. It's much more mathematical and much more theoretical. But I have found that in terms of understanding algorithms, one of the best things you can do is implement them. So we will do a lot of programming. The assignment will be the Snake assignment, which is a competitive assignment, and we modify it every year, and we provide some template code for Java that will allow you to work on your Snake. And if you go to snake.ms.wits.ac.za, you can find details of this year's Snake competition. What I want you to do for next week is read chapters 1 and 2 and pay particular attention to chapter 2. I am, of course, going to go through it in a lecture, but I'll gloss over a lot of it because there is a textbook, and I'm going to assume that you've read it when we look at the next chapter. Okay, so keep your eyes open for stuff on Thursday and Friday where we'll have a lab and a tutorial. But this is all we're doing for this week. It's a nice gentle introduction, more just to say this is what the course is about rather than to actually do any real work. In terms of the Snake game, this is what the 2020 version looks like. So I don't know if you remember this game, if you've ever played this game. You guys, I used to always say this is the game that runs on Nokia phones. But that analogy is getting less and less useful, as some of you probably have never seen a Nokia phone, let alone played games on one. But the idea is there are these snakes on the screen. In this case, there's a green one, a red one, a yellow one, and a blue one. And they all try to eat the apple. When they eat the apple, their length grows. Okay? So the winner of the game is the one that has the longest length. Okay, but we don't measure the length at the end of the game. We measure the length at the point at which the snake had its longest length, right? So if at any point in the game, the red guy had a length of 50 and that was his biggest length, and the green guy had a length of 40, that means the red guy beat the green guy, even though they didn't have that length at the same time, right? It's just their longest length at any point. There are some rules that we change every year to keep the game fresh and interesting. One rule that's changed this year is that there are now obstacles in the game. Last year there weren't obstacles, there were zombie snakes. So there's some obstacles in the game, and you've got to avoid them. If you bump into anything, you die. And the other modification is that the apple rots. So you'll see that, I don't know if you can see it on the recording, but you'll be able to see it if you download and watch the game from the website. The apple is changing color slowly, and what this is indicating is going from red to green. It's indicating that it's rotting, and as it rots, its value decreases. So if you manage to eat it when it's really fresh, your snake will grow by a lot, and if you only manage to eat it by the time it's like gotten sort of slightly green, your snake length won't grow by much. And if you eat it when it's green, like totally green, it'll kill you. Okay, the parameters of this are established on the Snake game on the URL shown earlier. So what you'll be responsible for is writing the artificial intelligence for a snake. Okay. Then what you'll be doing is competing against everybody else's snakes on a server that is running the snake game, right? So the scoring works in a sort of league system. So there's only 4 snakes in each game, but fundamentally this means that you end up with divisions, right? So in any game, if you are the winner, you'll get pushed up into the league above you, and if you're the loser, you'll get pushed down into the league below you, and eventually you'll end up in the position you deserve. So for one thing, I hope this means that, I mean, obviously, chat about the assignment with your friends and all of that, but obviously if you help your friends too much, they're gonna beat you and get better marks than you, and you're gonna get lower marks. So how the marks work is they're determined by your position in the game. So if you're in the top 4, you'll get 110%, although I'm not sure the external will allow that. So for now, let's say if you're in the top 4, you'll get 100%. If you're in the top 10, you'll get, so the other 6 basically, you'll get 90%. If you're in the top 20, you'll get 80%, top 30, 70%, top 40, 60%. And subsequently, if you beat the agents that are displayed here, you'll get 60%. So sort of your minimum mark for beating these guys is 60%. And anything above 60% comes from beating your classmates. Okay, so yeah, this was just to introduce the snake game. We'll talk a lot more about it as the term progresses, because there's a bunch of like cool strategies that you can use, and like I hope you guys will also come up with some crazy ones. In previous years, we had some students who did some very weird things and very impressive things. Like, so obviously the idea is to eat the apple and to not die, right? The best strategies are ones that focus on not dying. So eating the apple is important, but it's not as important as not dying. But we had students who came up with some very clever things. Like we had one student who had a strategy where if he was ever the longest snake in the game, then that means like if the game ended then he would win. So what he would do then is he would stop trying to eat the apple. He would just surround the apple to make sure no one else could eat it. And I was like, that's really clever. Like, whatever you can come up with is good. Steve, you all know Steve. Steve was a madman. Steve decided to try and hack the random number generator. So, when computers generate numbers, it's not entirely random. So if you can figure out some characteristics of the numbers that are coming out, you can predict what the next number is going to be. And so you could potentially predict where the next apple is going to spawn. And and then you could use that to your advantage. It's an utterly insane thing to do, but yeah, whatever you can come up with is fine. Okay, so I hope that sort of made the course a little bit more clear in terms of what we're going to do. Like I say, there will be a lot of math in it. There's a lot of proofs. There's a lot of calculations. There's a lot of equations that we'll be following. So if the fact that you're seeing my face makes you think that this is similar to mobile computing, just be aware that it's not, right? So this is not going to be a similar experience to mobile computing, apart from the fact that I'm the lecturer. Okay, but I hope we're going to have a lot of fun together. And I hope to see you in the WhatsApp group.